Javiers. This is Dr. S. Srinivas, Professor of Physics, Mrs. Avian College, Visakhapatnam. In this video, I would like to explain about Maxwell's equations and electromagnetic waves. The main objectives of this video is to understand about the displacement current and to know the importance of the basic laws of electricity and magnetism and how they are used to develop the Maxwell's equations, and also to understand about electromagnetic waves. And the learning outcomes of this video are the students can able to have a knowledge after watching this video about the displacement current, and also they know about Maxwell's equations. They have a skill. They got a skill to convert the integral form into the differential form, and also they are able to know the modification of the Ampere's law. But the students must have a few prerequisites to understand this video in a better way about all the basic fundamental laws like Gauss law in electricity and magnetism, Faraday's law in electromagnetic induction, Ampere's law in electromagnetism. Also, students must know Gauss divergence theorem, Stokes theorem in the vector analysis to convert one integral form into the another form. And now come to the topic. There is a Maxwell's equations and electromagnetic waves. We know electromagnetic waves are very popular and very important, and they play a very important role in the modern communication and technology. But how those electromagnetic waves are developed, their properties, their applications, nature, all those things can be understand mathematically, analytically by using the popular equations are named as the Maxwell's equations. So the Maxwell's equations plays a vital role in the study of electromagnetic waves. What are these Maxwell's equations? In fact, the scientist Maxwell did not prepare any new equations. He didn't derive any equations, but he considered four fundamental laws in the basic electricity, magnetism and electromagnetism, like Gauss law in electricity, Gauss law in magnetism, Faraday's law in electromagnetic induction, and further Ampere's law in electromagnetism. And these four fundamental laws are written as a set of laws, and their mathematical form are written as a set of equations, and those equations are named as the Maxwell's equations. But we know the Gauss law in electricity is developed for the static electric field. Gauss law in magnetism is developed for the static magnetic field, whereas Faraday's law and Ampere's law, they are developed for the steadily varying electric and magnetic fields. Whereas whenever the electromagnetic waves are propagating through a medium or a vacuum or a free space, a rapidly varying electromagnetic fields are associated with them. Means electromagnetic waves are always associated with the rapidly varying electric and magnetic fields. And the scientist Maxwell considered four equations from the basic laws and made a little modifications, and then they are going to apply for the electric and magnetic fields which are steadily varying or rapidly varying. That's where the Maxwell's equations can able to applicable for the electromagnetic waves. But before we are going to discuss about the Maxwell's equations, we should understand a very important concept which is called the displacement current. So now we are going to discuss about the displacement current. So what is basically the displacement current? To understand about that, let us start with Ampere's law in electromagnetism. You know, Ampere's is developed only for the steady currents. So whenever current is flowing through a wire, around the wire, the magnetic field is developed, and it can be represented mathematically by the formula closed line integral E bar dot dl bar is equal to mu naught I, where I is the current flowing through a wire, and B is the magnetic field developed around it. And its differential form can be represented like this. Is a del cross B bar equal to mu naught J. Here J is called the current density, the amount of current flowing per unit cross section of a wire. And we know mu naught is nothing but it is the permeability of the free space, and B is the magnetic field induction developed around the wire when current is flowing through a wire according to the Ampere's law. So then in fact, our aim is to discuss about the displacement current. We are in the process to understand what is displacement current by using this Ampere's law. Okay, so this is actually a differential form of the Ampere's law. And now take the divergence for this Ampere's law, which is in differential form. So divergence means del dot. So del dot del cross B equal to this mu naught is a constant value into del dot J. See here we have on the left hand side del dot del cross B means div curl B bar. Divergence of curl of any vector is 0. That's why the left hand side is 0. So right hand side term also becomes 0. But mu naught is not 0, having its own value. We know the mu naught value is 4 pi into 10 power minus 1 Henry per meter. That's why del dot J must be equal to 0. And this del dot J equal to 0 or the div J equal to 0 is called equation of continuity for the steady currents, because the Ampere's law is developed only for the steady currents. So it is called the equation of continuity for steady currents. But we know the general equation of continuity is like this: del dot J plus dou rho by dou T equal to 0. See, this is the equation of continuity for steady currents, and this is the equation of continuity, a general equation of continuity, which is applicable for any type of current. So there is some error in this equation. See, some term is missed. Here del dot J equal to 0, but here del dot J plus dou rho by dou T equal to 0. So some term is missed in the Ampere's law. So, and that correction is made by the Maxwell by using the concept of the displacement current. Since some term is missed here, so the scientist Maxwell thought to add some additional term to the J, because here del dot J plus something is there. That something is missed in this equation, which is actually from the Ampere's law. So to correct the Ampere's law, the scientist Maxwell thought to add some term like a J suffix D, and this J suffix D is called this is the displacement current term. I will explain you. But here, therefore, this equation, this del dot J equal to 0 equation now written as del dot J plus JD equal to 0, because we added JD to the J. So some term is missed, we identified here. That's why we added this missed term as a JD. So what is this JD means? J means current density, and this JD is called displacement current density. It is related to the displacement current. What is displacement current? So displacement current concept is introduced by the Maxwell in such a way: the varying electric field or the change in electric field is considered as a current, and that current is named as displacement current. Okay, so changing electric field is equivalent to a current. So whenever the electric field is changes, and the changing electric field is considered as a current, and that current is called displacement current. See, in fact, this displacement current will exist as long as an electric field is changing. Once the electric field stops to change, then automatically the displacement current will not be exist there. Okay, and this displacement current also produces the magnetic effects as same as the ordinary conduction current, because we know according to the Biot-Savart's law or the Ampere's law, whenever current is flowing through a wire, around the wire the magnetic field is developed. So not only by means of this conduction current, but also by means of this displacement current, we can have the magnetic effects. The displacement current also can able to produce the magnetic effects as same as the ordinary conduction current. And to understand better way about this displacement current, let me take one example that is called capacitor. We know either parallel plate capacitor or any type of capacitor. We know the usually capacitors are in a two different modes, either charging or the discharging. Whenever capacitor is charging, the plates charge, I mean the charge on the plates is increases, and the electric field intensity or the electric field strength around the plates is increases. Whenever the capacitor is under discharging mode, then the charge on the plates is decreases. So the electric field strength around the plates will be decreases. So either increase or decrease during charging and discharging of the capacitor, the electric field is changing. The electric field between the plates of the capacitor is changing either during charging process or discharging process. So since the electric field is changing between the plates, so between the plates a current is existing. That current is nothing but displacement current. That's why any electric circuit consists the capacitors, though the capacitor plates are apart, separated either by free space or air or some dielectric, the current can able to flow from one plate to another plate. That is only because of change in electric field. That is called the displacement current. So to formulate this displacement current, let us start with Gauss law. We know basically Gauss law, but here I considered the Gauss law in a differential form. The div d bar equal to rho, where d is called the electric displacement vector and rho is called the current density. Is the charge density. It's the electric displacement vector and charge density is a charge present per unit volume. Okay, now take differentiation of this equation on both sides with respect to t. So here d we are differentiating with respect to t. Here we have the rho charge density with respect to time we are differentiating. But del cannot be differentiable with respect to t because del is constant with respect to t. Del can be variable only with respect to x, y, z coordinates. Okay. So then we have this equation. Now add div j on both sides for left hand side and right hand side. Well, so div j we added on both sides. And see, this is the general equation of continuity we mentioned here. Del dot j plus dou rho by dot equal to 0. That's why we considered this is the 0. And we take del dot as a common and we got del dot j plus dou by dot. See here, actually, very beginning we explained from the Ampere's law, we got only del dot j equal to 0. Maxwell postulated some term is missed and that term is taken as a JD and which is called the displacement current density, and now we found the value of JD as a dou d by dou t. Hence the displacement current density JD is equal to dou d by dou t. We know displacement current density JD can be written as a dou d by dou t, where d is called the displacement vector. So displacement vector d equal to epsilon naught into E bar is electric field intensity. It is the permittivity of the free space. So we can write like this. So this is actually formula for displacement current density. So actually the Ampere's law is very beginning we considered del cross B bar equal to mu naught J, but now J is replaced with J plus JD, and JD is nothing but dou d by dou t. So this equation now can be written as del cross B equal to mu naught J is a old equation before modification by the Maxwell, but after modification mu naught into J plus JD means dou d by dou t. But dou d by dou t means we know epsilon naught into dou E by dou t we written here like this. Okay, so this is actually modified Ampere's law. Del cross B bar equal to mu naught into J plus epsilon naught dou E by dou t. So this is about the displacement current. And now we are going to discuss about the Maxwell's equations. You know, already I mentioned scientist Maxwell does not derive any equations, any new equations. He considered 4 fundamental laws in the electricity, magnetism and electromagnetism, and their mathematical forms written as a group or a set of equations, and those equations are named as Maxwell's equations. They are used to study about electromagnetic waves, their properties, applications and nature. So what are the four fundamental equations here? Means the first fundamental equation Maxwell considered from the electricity, that is nothing but Gauss law of electrostatics. We know this is actually a mathematical form of the Gauss law of electrostatics, and we know the statement. This integral E bar dot ds means is a flux phi e, flux equal to q by epsilon naught. It means that the statement is like this: the total normal electric flux over a closed surface is equal to 1 by epsilon naught times the charge present within the surface. Let us consider one surface which includes a certain charge. Then the total flux passing through that closed surface is equal to 1 by epsilon naught times the charge present within the surface. See, the flux is always related to the charge inside the surface. It means inside the surface there is a positive charge, the electric lines of forces or the flux is outwards. Inside the charge is a negative charge, the electric lines of forces or flux is inwards. There is a more charge, more flux, more lines of force are passing, less charge, less flux, no charge, no flux. This is basically Gauss law. Okay, and this equation is considered as a first basic Maxwell equation. And the second equation is taken by the Maxwell from Gauss law of magnetostatics. So this is also related to the flux, but it's a magnetic flux. So it states that the total magnetic flux over a closed surface is 0. See, this is the total electric flux is not 0. It's 1 by epsilon naught times the charge present within the surface, but the total magnetic flux is 0. Because there is no monopole in the magnetism. Magnetic field is always continuous. All magnetic lines of forces are closed loops. That's why the Gauss law of magnetostatics states like this: the total magnetic flux over a closed surface is always equal to 0, and magnetic flux is always equal to 0, and this is taken as a second fundamental Maxwell equation. And then come to the third one. It is nothing but Maxwell third equation is taken from Faraday's law of electromagnetic induction. You know, according to the Faraday's law, whenever the magnetic flux linked with the coil or a closed circuit changes, an EMF is developed in that circuit. An electric field is established. It means using magnetic field changes, we can able to produce electricity or electric field. So that is actually Faraday's law, and this equation, this Faraday's law in mathematical form is considered as a third fundamental Maxwell equation. Of course, here this negative sign can be explained by the Lenz's law in electromagnetic induction. And finally, the fourth Maxwell equation is taken from or considered from the Ampere's law. We already mentioned this is actually Ampere's law. Whenever current is flowing through a wire, around the wire the magnetic field is developed. It means electricity to magnetism. So this is actually from magnetism to electricity, and this is electricity to magnetism. Okay, so we can able to produce the magnetic field by using the current. Okay, so magnetic field can be developed around a wire. Wire consists of the current. So this is basically Ampere's law, and this mathematical form of the Ampere's law can be considered as a fourth fundamental Maxwell equation. It's a fourth fundamental Maxwell equation. And then finally, see, this is the first Maxwell equation, is the second Maxwell equation, is the third Maxwell equation, is the fourth Maxwell equation. All these four are named as the fundamental equations. All are in integral form. So they are also named as Maxwell's equations of integral form. But these four equations cannot be applied as is in the study of electromagnetic waves. We need to convert them into the differential form. They are basically in integral form. We should convert them into the differential form, and those differential forms, the equations which are in differential forms are widely used to study the electromagnetic waves, because more flexible equations are those. That's why we are going to use those four equations in the study of electromagnetic waves. How we can convert these equations means only by using the vector theorems. In our vector analysis, we have two very important theorems, which is called Gauss divergence theorem and Stokes theorem. Gauss divergence theorem is used to convert the double integration, the surface integration into volume integration, means triple integration, and vice versa. And the Stokes theorem used it to convert the line integration, means single integration, into surface integration, means double integration, and vice versa. In fact, in these four equations, the first equation means this is the first fundamental Maxwell equation, which is in integral form, and this can be converted into the differential form by using the Gauss divergence theorem. And the second fundamental Maxwell equation from the Gauss law of magnetostatics, this also can be converted into the differential form by using Gauss divergence theorem. But the Faraday's law, the mathematical form of the Faraday's law, or the third fundamental Maxwell equation, which is in integral form, and the fourth fundamental Maxwell equation, which is in integral form, both can be converted into their differential forms by using the Stokes theorem. So after converting all those four, we'll get these four equations. See, so this is basically div E bar equal to rho by epsilon naught. This is a div B bar equal to 0, curl E bar equal to minus dou B by dou T, curl B bar equal to mu naught into J plus epsilon naught dou E by dou T. And all these four are basically, this is actually Gauss law in electrostatics, but in differential form. This is the Gauss law in magnetostatics in differential form. This is the Faraday's law in differential form. This is the Ampere's law in differential form. And these four equations are now considered as Maxwell's equations of differential form. And now, for our convenience, I am comparing both the equations here, both integral form and differential form. See here, this is actually the integral form of Gauss law, is a differential form of Gauss law. It is the integral form of Gauss law in magnetostatics, it is a differential form of Gauss law in magnetostatics. It is the integral form of the Faraday's law, it is a differential form of the Faraday's law. It is the integral form of the Ampere's law, it is a differential form and corrected differential form of the Ampere's law, and this correction is made by the Maxwell. This Ampere's law is corrected by the Maxwell by using the concept of the displacement current. So, and these are actually widely named as Maxwell's equations, but out of these two sets, and these differential form equations are very, very important, because these differential form equations, which are widely named as Maxwell's equations, and these equations are very flexible to study the electromagnetic waves properties, nature, and applications analytically and mathematically. So this is about Maxwell's equations and electromagnetic waves, and thank you.